Welcome to the chapter 13 video where we're going to discuss soil. We're going to talk about characteristics of soil, how soil forms, soil properties, and then we're going to look at its uses. And so in this chapter, our outline is going to be as follows. So we're going to look at the study of soil as a science, so soil science, talk about specific geologic processes, how they're related to soil formation. We're going to talk about the process of soil formation, soil properties. We're going to look at the soil profile, so basically how the soil layers can be, soil erosion, and then soil conservation. And then we'll mention some different ag practices where you can do conventional tillage, which is where you use big tractors, to till up the land, or we can do conservation tillage, and we'll talk about what those are and what the differences are, and then we'll look at the protecting the soil on lands that aren't used for ag or for farming. Okay, so soil science. Soil science is the study of soil as a natural resource. Okay, and so this particular field studies soil and learns about how it forms. So it wants to know about the soil formation. We classify soils based off of different characteristics and properties of those soils. And we want to map those soils. We want to know where exactly the different types of soils are located. We are interested in the physical, chemical, biological properties of soils, as well as the fertility. So how fertile are those soils for growing plants or crops? And we are interested in knowing all of this information so we can use the soils and manage the soils. Okay. And so in an ideal world where we know a lot of this information and we use that to use the soils as a resource, but to manage them in a way that we're not degrading those soils so much that they, we destroy their profile, we change the properties, we change the functions of the soils, and we degrade the fertility. Okay, so that's what we're trying to avoid when we look at management of soils, and we'll talk all about this throughout the chapter. Now, in order to understand soils, we are first just going to briefly talk about geology and then the formation of soils. And so the earth itself is made up of different layers. And so you have the crust, which is basically what we're living on, and it's the thinnest layer. It's a very thin layer compared to the other layers. Then you have the mantle, and the mantle can be broken down into a solid mantle that's underneath the crust, and that solid mantle and the crust makes up the lithosphere. And then underneath the solid mantle you have the asthenosphere, which is what's known as the plastic part. So basically it's movable and malleable because of the heat and pressure. Excuse me, because of the heat and pressure in this area of the mantle. And then the mantle continues downward until you reach the core. And so the core is separated into an outer core and an inner core. Okay. And now the crust can be divided into continental crust or oceanic crust. And that's important because of the different types of plate boundaries, whether you have continental, oceanic, whether they're moving away from each other, colliding, or sliding past, determines the type of plate boundaries that you get. And whenever I say plate boundaries, I'm referring to the tectonic plates and where they meet with other tectonic plates. So for example, you have the North American plate, right, which is this area here. And the North American plate is adjacent to the Pacific plate, the Caribbean plate, and the African plate and the Eurasian plate. Okay, and these plates are constantly in motion and they're moving in different directions. So for example, We have an arrow here showing the Indian plate moving into the Eurasian plate. We have the Indian Australian plate moving into the lower portion of the Eurasian plate. The Pacific plate is moving in this direction. Right? The Nazca plate's moving and colliding with the South American plate. And so the plates are constantly in motion, but they're moving at a fairly slow pace relative to how fast we think about motion. You know, only like a couple millimeters or centimeters per year, depending on the plate. And so these plates can cause specific boundaries. And we'll talk about that in a little bit, but basically, if they're colliding together, you get a type of boundary. If they're moving away, you get a divergent boundary, and then they can be sliding past one another to give you a different type of boundary. And so, like I mentioned, the different layers of the crust, or the Earth's layers, out of those layers, the crust is really thin and less dense, covering over the mantle. The mantle actually makes up most of the Earth, as we saw in this image, and it surrounds the core of the Earth, which is iron. And like I mentioned, the outermost portion of the mantle is solid, but then under that solid portion is the plastic portion of the mantle, which is malleable and allows for flow. Think of it as like molten lava under there. And that's the asthenosphere. So the crust and the solid outer mantle makes up the lithosphere. The mantle underneath that, the plastic, is the asthenosphere. Okay. And the plates that are of or make up the Earth's crust moves over the surface of that liquid mantle very slowly. And so the movement comes from the heat of the Earth, and the plates, like I mentioned, can be pulling away from each other, they can be colliding, or they can be moving past one another. And so there are three types of plate boundaries. One is convergent. That's when two plates are colliding with one another, and that can lead to the formation of mountains. All right, so like the Indian plate colliding with the Eurasian plate, that gives you the Himalayas. Okay. Then you have divergent boundaries, where two plates are moving away from one another. And a common area where that is happening is actually in the Rift Valley in Africa. So this area is moving in opposite directions, and the Mid-Atlantic Ridge. So these plates are moving in these directions, and so there's actually this crust is splitting, and underneath the Earth's surface, magma comes out, solidifies when it hits the colder water, and makes new ocean floor. And then the third form, or the third type of plate boundaries, are transform boundaries. See if I can get that M to come up. There we go. And that's when your plates are sliding past one another. And the San Andreas Fault is actually a transform boundary. And so this boundary here, you have one plate moving in one direction, and then the Pacific plate moving in this upward direction. And so they're sliding past one another, kind of causing them to grind against each other. And so they can lead to different characteristics. So for example, divergent causes magma to come up because splitting from the Earth. Transform, you're sliding past and grinding, so you can get earthquakes. Convergent, you get earthquakes. But then you can also have two different types of convergent boundaries, where you have collision and subduction. So if it's two continental boundaries, then, or continental plates, you get mountain formation relatively, like the Himalayas and the Indian. But if you have an oceanic boundary, right, an O, with a continental boundary, that oceanic crust is more dense than the continental crust. And so it will actually subduct underneath and cause magma to come up as it melts, and you can get volcanoes. Um, and you can get earthquakes. You can get actually deep earthquakes because they can slip and cause, deeper earthquakes there. Some of the places where you see these type of boundaries is the Pacific Ring of Fire. So all of these are subduction boundaries where you have oceanic plate going underneath continental plate, and that's why you get a lot of volcanoes in this area. Okay. And so those are the three type of plate boundaries that exist. Now, other geological processes that exist that are more related to soil formation are weathering and erosional processes. So chemical weathering is basically where you have the chemical alteration of rock where it will fragment and dissolve because of that chemical alteration. So for example, if you have rock fragments exposed to the atmosphere, those rock fragments can oxidize and they can break down. Whenever those rocks will loosen or become redistributed, so if those fragments are redistributed across the landscape, that's referred to as erosion. Okay. There's also a type of physical or mechanical weathering that we'll go ahead and talk about here. And so weathering is where you reduce the size of the particles by moving with water or air. And this is kind of that mechanical or physical weathering. And so they're not changing the chemical nature of the rock, they're just breaking it down. And so this is like freeze thawing cycles, or this is, plants and animals kind of growing in or affecting the rocks to where they're breaking those rocks down. And so here's an example of freeze thawing where you have a rock with cracks in it. And if moisture gets in those cracks, it can freeze. And ice is actually not as dense as water. The molecules actually expand, and so that ice will expand in those cracks, causing them to become larger. And then if that happens again, it will continue over and over until it breaks that rock into smaller fragments. And so the Grand Canyon is an example of a really eroded landscape where water, wind, and other physical forces, animals potentially, have caused that landscape to erode, and all of that sediment will flow down slope. So the erosion will follow kind of those gravitational forces and go from high areas to lower areas. Okay. And so all of those two processes, so the physical, mechanical, and the chemical weathering in combination with erosion, is really important for soil formation because the the type of soil that you get is based on the type of parent material that you begin with, and we'll look at that in the next couple of slides. And by parent material, I mean the type of rock that you start with. So for example, if you have granite rock, like in the Sierras, that granite rock will erode and break down and contribute to a specific type of soil. If you have serpentine rock, which is a kind of a rarer form of rock, it is high in magnesium, low in calcium. I think it's magnesium. And so those type of minerals aren't really good for plant growth, but there are specific types of plants that can grow in that serpentine soil. And so the soil chemistry is going to be based off of the type of rocks that it's made up of, so that parent material. Now, if we look at land in general, right, we know that land is the area that's not covered by water. And on the land, you can have soil. And so not all the land is covered with soil. It could be rocky areas. But soil is a mixture of minerals, organic material, living organisms, air, and water that support plant life. So a good agricultural soil will have this specific ratio of materials, so organic matter, water, air, and minerals. Now, specifically for soil formation, the way soil forms is based off of these different factors. And these factors you can remember using the acronym CLORT. Let me actually write it a different way. So for these you can remember like this. So CL is for climate. O is for organisms or biological factors. R is for relief, which is also topography. Okay. P is for parent material, and T is for time. Okay, and so we're going to talk about each of these factors over the next two slides. So soil formation, like I mentioned, begins with parent material. And the parent material is going to determine the chemistry of the soil. So the parent material is basically those ancient rock layers or more recent deposits, say from lava flows that have solidified or glacial activity. And the breakdown, the weathering of those rocks is going to cause that parent material to fragment and to start being broken down. And if you remember about succession, in primary succession, the lichen will attach to those rocks and start to break it down to start that soil formation process. Now, rocks can break down through freeze-thaw weathering, through wind, through water, etc. It doesn't have to specifically be biological organisms. But now, once you start getting a thin layer of material to form from that parent material, organisms can then come in and modify that parent material. So lichens can actually grow on the rocks. But then when you start to get that thinner layer, then say your herbs and your forbs, maybe bacteria or other organisms can come in and start altering the underlying rock layers. And so now that soil formation process is really starting to happen. And then the humus is basically the organic material that you get after the living organisms have been there for, say, several years and they've died and grew back and died. And you have that decay of the plant and animal remains that mixes with the materials from the parent material rock layers, and in combination with that parent material and the organic material, you get nutrients that the plants need. And it also creates this soil that has air spaces in between the particles that allow for water absorption and water drainage. And then you combine that with burrowing animals such as earthworms or gophers or whatever else that may burrow, can bring nutrients from deeper soil layers, or it can cause the soil to be aerated because they're constantly mixing that soil. And so just to kind of go back and summarize, you really have your starting parent material, right? Whatever rock that is determines the minerals that are going to be in that soil layer. Now you combine that with climate, so water, wind, whether it's hot, whether it's cold, is going to break down that parent material with biological factors. And that happens over a long period of time. Right? And then depending on the relief, the topography, it determines where that soil is going to be deposited. So for example, if you have kind of a landscape like this, right? You'll have erosion that will cause soil to deposit here. And so you'll eventually get some soil build up there. You might get some soil build up here. This area will build up soil and fill in. this can have erosion this way and this way. And so you'll get soil build up here. And so this area up here won't really have soil because it will always be eroding down. And same thing on this side, it will erode down and you'll get kind of soil deposits down in here. And so that topography or the relief determines where that soil is going to form and where it's going to be deposited. So all of these factors working together leads to soil formation. Okay. Now we can look at soil, and soil will have certain properties based on the parent material and the organic matter that's been mixed with it. So soil texture is basically telling you the size of the mineral particles within the soil. If it is a lot of large particles, then you're going to have sand and gravel. If it's a lot of small particles, it's primarily clay. So think about it this way. If you have really large particles, right, there's going to be space in between those particles because they're large and they can't really pack tightly together. And they're not going to be perfectly spherical. They'll have edges on them that prevents them from packing. So your water is going to move through these spaces relatively quickly. If you've ever been to the beach and you've seen the sand, the water go through the sand on the beach, it goes through really fast. Or if you've ever had sand in your yard and you've poured water in it, it just kind of leaches through really fast, right? Whereas clay is a bunch of smaller particles packed tightly together, and there's hardly any space in between that. If you pour water on clay, it basically kind of sits and it doesn't drain very well. That's based off of the spaces between those soil particles, and that's really determined by texture. And so the soil structure basically refers to the way those particles clump together. So the ideal soil for agriculture is a loamy soil. So this loamy soil has good aeration and drainage properties because it has large particles with nutrient that allows nutrient retention, but it also has some clay particles, and so it has water holding capacity. So it has a combination of, say, clay and sand and silt that allows it to have a little bit of the characteristics of each of those different types of particles. But now when you start getting, say, on the sandy side, then you start to lose that water holding capacity. You have good air, but you don't have any good water holding capacity. And so in good soils, 1/2 to 2/3 of the space contain air after that water has drained. If that soil crumbles really easily, it's known as a friable soil. Okay. And then a lot of the organisms that live in soils are things like earthworms, insects. You can have bacteria, algae, protozoa, nematodes, etc. So soil communities or epiphytic communities are really interesting and actually really complex. And so this pyramid is a soil texture pyramid. And basically you would look at a sample of of soil, and let's say you dig up a area in your backyard and you get it analyzed, and somebody says, okay, it's 40% silt, 40% sand, and 20% clay. Now you can use this to determine what type of soil you have. So this right side is the silt side, the bottom side is the sand, and then this side is the clay. And so you say, okay, I have 40% silt. So you go find 40% on the silt side, and you see these lines. You basically follow the lines across. And so this line here is the 40% line for silt. Then you say, okay, I have 40% sand. So you come here, you find the sand. So this line here is 40% sand. I can't draw. Okay, so now we've got these two. So that means there 80% is silt and sand. So the remaining 20% has to be clay, which is what we determined. So you find the 20% clay, you come over, and where those meet, it tells you what type of soil you have. So this is a loamy soil, okay? And so if I said, okay, what is a 20% silt, a 30% sand, and a 50% clay, what type of soil is that? So what you would do is you would find, let's say, silt, go to 20. So this is your 20% line. Then you go to sand, you find your 30% line, which is this one. Then you go to clay and find your 50% line. All right, so we'll draw these down, we'll connect, connect there, so they're right in here. So you have a clay soil texture, okay? And so just to do one more, let's say we have 70% sand, 10% clay, and what do we have left? 20% silt. Okay. Let me get rid of these lines. All right, so what we would do is we would just follow that same method. Let's start with sand. So here's sand, 20% silt, 10% clay. So you carry these over. All right, so we have a sandy loam. Okay, so that's the type of soil texture you would have. So that's how you determine soil texture using these texture pyramids. Now here's an example of just soil organisms. So you have all kinds of fungi, you have organic material being incorporated into the soils by your decomposers and your bacteria. You have bacteria and algae, protozoans, fungi, you have earthworms, lots of different invertebrates. And so the soil communities are actually really complex, and a healthy soil community is really important for the ecosystem to function and basically be healthy itself. There are a lot of different major soil types, depending on where you are around the globe, and that soil type depends on the caloric factors. So what parent material is being broken down, how much organic material is being incorporated into that soil, how much rain is present, because rain affects leaching and the weathering process. And is it hot? Is it humid? Is it dry? Does it snow? Is it cold? And so a lot of those affect the different types of soils that you'll find, because again, climate, organisms, parent material, all of those are important during the soil formation process. And so when we look at the different soil types, the first thing we're going to really look at is the soil profile. And the profile is just the horizontal layers of the soil. And the horizontal layers have various chemical compositions, physical properties, particle size, and different amounts of organic material. And each layer that you can look at and distinctly define is known as a horizon. So a soil profile is made up of different soil horizons. And so the top horizon will be the topsoil. That is your A horizon. Above the A horizon, you have all of the organic debris, the leaf litter. So that is the O horizon. Okay, so the organic layer. The A horizon is underneath that, and that has maximum, not minimum. So that has a lot of biological activity. Right? This is where a lot of your living organisms are located, in that O and A horizon. These horizons are really dark colored, a lot of organic material. The O horizon is primarily organic material. Your A horizon starts to become organic material mixed with mineral matter. Now, rain will cause leaching of soluble minerals. So basically, minerals that dissolve in the water will be leached down from the A horizon into the E horizon. And so leaching will remove soluble minerals, right? And then underneath the E horizon, you'll get the B horizon, where the accumulation of those materials or those minerals will occur. So you get accumulation of silicate, clay, iron, organic matter that has leached from those upper horizons to basically be suspended in the B horizon. The C horizon is where you have the parent material, and this is kind of what's leading to the formation of the soils. And so this was the parent material that has eroded and contributed to the upper soil layers. And then underneath that, you have that hard bedrock that the parent material is basically derived from. And so in general, you have your O, A, E, B, C, and R. Okay, so organic, you have your organic mixed with mineral, your mainly minerals leaching, right? Accumulation of your minerals here. Here's your parent material, and then here's your bedrock. Okay. In terms of soil classification, you have 15,000 separate soil types in North America alone. Cultivated land is generally classified as either grassland or forest soil. Grasslands are interesting because they really have a deep topsoil layer and a lack of leaching. And so you get a thin subsoil. Let's see if I think I have an image here. So this is typical grassland. So big organic layer with thinner subsoil layers. And again, that's because a lot of organic matter, because that grass grows a lot, dies every year, and that organic material builds up. In forest soils, however, you usually have a lot of rainfall, so the topsoil is relatively thin, but the subsoil is where a lot of the root growth happens, because you have a lot of leaching down into that subsoil layer. And so like we mentioned, that O horizon is made up of leaf litter, undecomposed or partially decomposed organic material. A is the topsoil. It contains most of the nutrients and living organisms. Remember, organic with a lot of minerals. E is formed from the leaching of the darker materials. And so that E is usually nutrient poor. And then below that, you have your B horizon, which is the subsoil. Okay. And so remember, in grasslands, this layer is relatively thin, and it contains less organic matter, fewer organisms, but this is where your nutrients are becoming accumulated from the topsoil. The C horizon's that parent material, and then the R horizon is the bedrock material. So there are two features of tropical rainforests that really influence the nature of soils. So for example, in tropical rainforests, you have high temperatures. So you get a very fast decomposition, little leaf litter that accumulates on the surface. High rainfall causes all of that nutrients to leach out of those upper layers and not really be accessible to plants. And so that's why whenever we talked about tropical rainforests, we mentioned that even though there's a lot of species and a lot of plant growth and biomass, the soils are really nutrient poor. And it's because of these factors, these parts of chlorp that are affecting that soil formation process. Okay, so moving on, in terms of soil formation, erosion is a big factor in the formation process, and that's because erosion is where the sediments are worn away and transported by wind, water, or ice, so the portions of the soil. And worldwide, so globally, erosion is moving 2.5 bill or 25.4, not 2.5, 25.4 billion metric tons of soil per year. There's a lot of soil being moved around by, natural forces. This erosion is actually increased because of human impacts such as deforestation and desertification. So whenever we remove vegetation off the landscape, that allows that vegetation to be eroded and removed, um, because the roots in the vegetation, the grass, the trees, the shrubs, hold all that soil in place. If you've ever pulled up a weed or pulled up a plant, you'll know that the roots will bring up a lot of soil that's kind of attached to it. And so you imagine if every plant does that, it holds that soil in place. Now, if you remove those roots, all of a sudden those soil particles are loose. They can be moved around. And so that was one of the big factors that led to the Dust Bowl in the early 1900s, was the increase in ag. And when there's no crops on the fields, you get winds that blow that soil around. And so that's kind of what happened. And so poor agricultural practices lead to increased erosion and lead to not only the erosion of these soil particles, but the things that are in those soil particles and in the soil itself, such as fertilizers and pesticides. So they don't stay on the fields, they actually get transported into various habitats. And what's pretty crazy is, you've probably heard of it. The news was talking about it quite a bit. I think it was last year or the year before. But soil particles can actually be blown around the world. And so, for example, the sediments from the Saharan desert can be blown across the Atlantic Ocean and deposited on North America. And so what we put in the soil is not just maintained or contained locally. It can move globally, because of those atmospheric and wind processes, which is pretty insane to think about. Um, Most agricultural practices lose soil, so they do what's called loose soil faster than it can be replenished. So we're basically using up the fertilizer, breaking that soil down faster than the soil can be made. Um, and the water erosion is one of the premier kind of erosional forces that we really can see. Um, like I had mentioned, wind erosion is really common in dry, treeless areas, and wind erosion is really big in the Great Plains. Open, lots of wind. So that's kind of where the Dust Bowls have happened. So they've had 4 serious episodes of wind erosion since the 1800s. And so that's kind of a big issue, in terms of the erosional sector of soil formation. Now, we can practice soil conservation and prevent a lot of the issues that we've mentioned. Um, and one of the key things is that when you lose the topsoil, the fertility is pretty much gone. And that's why we need fertilizers, is because we've planted on that field, we've overused its resources, and the land still needs to be, um, used for ag land, but the fertility is dramatically reduced because when you grow a crop, you put that crop down, you grow it, and then you harvest it, and you don't allow that organic material to go back into the soil because we're shipping that organic material to other places and removing it off the surface of the field. And so none of the nutrients is being recycled. That organic matter is not dying and being recycled back into the topsoil. And so eventually we will use the nutrients out of that topsoil, and we have to use fertilizer to basically restore it. Using fertilizer raises food costs because fertilizer costs money, but it also increases sediment load because we're destroying the topsoil, we're increasing erosion, and that sediment will flow whenever it rains into waterways and cause more sediment load in rivers, streams, and lakes. So over 20% of the land in the US is suitable for ag, but only 2% does not require some form of soil conservation practice. Now, if we look at agricultural potential globally, 11% of the land can be used for crops. 20% is permanent pasture. In the United States, we're looking at about 20 and 25% respectively. African continent, we're looking at 6 to 29% respectively. And so if we kind of look at this globally, terms of silt transportation, right, so sediment transportation because of runoff and erosion, these areas here, right, are less than 40 metric tons of silt. But you look where there's a lot of farming, right? 440 to 200, and then in the rainforest where there's a lot of deforestation, you get more than 200, where that fertile topsoil is carried away by rivers, by rainfall. And so what you essentially get is something that looks like this. And so there's, a lot of issues with how we run conventional agricultural practices in terms of maintaining the health of soil profiles and the soil that we're using to grow our food. Now, there are some soil quality management practices that we can do where we enhance organic matter. We try not to till as much and to break down that soil profile. We manage the pest and the nutrient cycles much more efficiently to kind of maintain that healthy ecosystem. We try to prevent soil compaction because if you compact that soil with heavy machinery, then the soil loses the amount of air capacity and water holding capacity because now the air spaces aren't as large between the particles because they've been compacted together. We want to keep the ground covered. We want some sort of vegetation on that ground at all times. And you want to diversify your cropping systems. That way you're not overusing the topsoil and overusing the fertile nutrients and minerals that are in those soils. Contour farming is one practice where you could till at right angles to the slope of the land, and each ridge basically acts as a small dam. And so you can do this on gentle slopes, and this kind of helps with soil erosion and prevents a lot of soil erosion. Strip farming is where you can alternate strips of closely sown crops to slow water flow, and this helps with water absorption and the maintenance of water across the landscape. You could also practice what's known as terracing, so you construct level areas at right angles to the slope, right? So it looks like the slope is here, there. So there's right angles is where that's constructed, and that helps retain water. And so this is really good when you have very steep land. So you're basically converting these level areas, again, to help with erosion. Waterways and windbreaks are also fairly useful, and so you can use those waterways to collect the water and to kind of divert that flow. Windbreaks are where you can plant trees around, say, fields to reduce the amount of wind that comes through. So you reduce that wind velocity, and so you're therefore reducing the amount of soil and topsoil that's going to be blown across the surface because of that wind. So this is the use of a waterway between two fields. And then here we can see some wind breaks that are helping to reduce that wind velocity moving across these pastures or these fields to help reduce the amount of erosion that occurs. And so one of the final things we want to mention is conventional versus conservation tillage. Now, plowing and tilling the land has a lot of key effects that farmers need and want. First, it gets rid of weeds and it buries those weed seeds. Crop residues are turned over, so what little bit of the crop is left is added to the soil. It mixes the soil, so leach nutrients are brought back up to the surface, and then that cooler, darker soil is brought back to the top and warm. So this is good for plants and growing plants. However, every time you plow the land, it basically adds expenses, and then it increases the amount of time that the soil is able to be eroded because there's no vegetation on that surface, on the topsoil. What you can practice is what's known as a reduced tillage. So you use less cultivation to control weeds and prepare soil, and in general you leave a percentage of the soil surface covered with a crop residue, and you kind of rotate the areas that have that crop residue. Now you can practice conservation tillage where you're leaving up to 30% or more, up to 30% or more of the soil surface covered. And what you can do is you can kind of practice several different versions of this conservation tillage depending on kind of what works. You can do a mulch tillage where you till the entire surface right before you plant. You can strip till, which is where you just till the strips that will receive the seeds and only those areas that have the seeds. Ridge tillage, it leaves ridges, the crops planted on the ridge with the residue left between the ridges, or you do no-till farming, where you have planters that place seeds in slits that are cut into the soil and you're not tilling that soil at all. Some of these aren't as cost effective as conventional tillage, which is why a lot of the farming practices still do that conventional tillage. However, the effects of reduced tillage is very substantial in terms of ecosystem health and soil maintenance. So wildlife can gain actually winter food and cover when those fields aren't in use. Less runoff means less silt entering the waterways. Row crops can be planted in sloped areas. If you have fewer trips over the field because you're not tilling as much, you use less energy. Two crops can be grown in a field that has been compared to the monoculture where you're only growing one crop. And if you're doing fewer trips, it's also less soil compaction, right? So not only is it less fuel, but it's also less soil compaction and you're maintaining the health of that soil profile. However, drawbacks to conservation tillage is that it can delay the warming of the soil. Crop residue reduces evaporation and upward movement of water, so that can affect the growth of plants. And then you can harbor plant pests, you could harbor diseases, which could eventually lead to more insecticides or fungicides because of the accumulation of plant residue that could harbor those things. So this is just a comparison of the various tillage methods. So if you do like conventional plowing, amount of fuel, time involved, reduced tillage, etc., to no tillage, right? You can kind of see those differences there. Now, when it comes to protecting soil on non-farm land, it really depends on kind of what you're using it for. So you can use appropriate soil conservation practices. Um, so you can use, say, land that's not usable for crops, for grazing. It can be used for wood production, wildlife, or aesthetic or recreational purposes. It just depends on, again, what the reason you're using, what the reason is for using that land in that particular time. Okay, and so that's it for chapter 13. So here are the summary slides for that chapter, or for this chapter. Remember, these are the main ideas, not everything you need to pay attention to in this chapter. So make sure you just kind of use them as a guide for when you study for your exams or your quizzes. And as always, let me know if you have any questions, if you have any concerns. You can contact me via email or through the course discussion board. And with that, we'll see you in the next chapter.